Today we are here to have some fun with lambdas. So actually this talk is based on Lambdas to the Slaughter, which is a talk given by Kevlin Henney on meeting CPP. This presentation will have the link to that talk, so if you want to watch, you can go watch that. Um, and with that, so here's the syntax of a lambda. It starts with square brackets, and inside that you can have capture arguments optionally. Then it's the same syntax as a function. You have a set of parentheses. Inside those parentheses, you have the parameters of the function, and after that you have a curly brackets, and the set of curly brackets contain the body of the function or the lambda. If you don't have any function parameters, a lambda can also be written as empty square brackets and then the body. The parentheses containing the function arguments are optional. And the thing about a lambda is that it is an expression. So you can assign variables to an expression. So you can write, for example, auto foo equal to square brackets parentheses. It takes a parameter f, which in this case is auto, and the body is just printing f. And if I call it like this, foo of 10, it will print 10. Why is lambda useful? Like, why even add a lambda when we already had functions, right? So let's take a simple example. I want to filter out the even numbers from a vector, right? So here's the code without lambdas. I have a function is even, which returns a boolean and takes an int. And if the integer mod 2 is 0, then it returns true. Otherwise, it returns false. So we have a list of a vector of numbers containing 1, 2, 3, 4, 5. And this is the vector that I want to populate with even numbers. I call this even nums. So we can use STL in this case. The algorithm is copyif. So we begin from the nums.begin and till nums.end. I'm using back inserter because this even nums is empty right now. So back inserter will give it an iterator which will insert the elements as we go on. And the fourth parameter finally is the function that if this function returns true, then it will insert then it will copy the value over in the second vector. So essentially we have a for loop, we and a predicate. The predicate is even. So we start from the first element. Is even will return false, so it will not be inserted. Then we go to 2. Is even will return true, so it will insert the element into even nums. Then 3, which will not be inserted. 4 will be inserted, and 5 will not be inserted. The same code with lambdas is slightly shorter. So we have nums with the same values. We have even nums. The copyif remains the same except for this one last part. Inside this, because it is an expression, we can directly give it to copyif. Just like we have a function which takes an int, we can directly give it 3. We don't need to have a variable for that. So we have a lambda which takes an I and it returns I mod 2 equals 0. So if the number is even, this will be true, and if the number is odd, this will be false. So both this and this earlier one will have the same behavior, but this is slightly more concise than the other one. One other very important aspect of a lambda is you don't need to store it in a variable. You can declare a lambda and just immediately invoke it to just get the result. So this is a very dummy example. So I have a version variable which is an int, and I assign it to a lambda which returns 5 and then immediately invoke it. Int cannot be int version cannot hold a lambda, but it can the value can be the result of declaring a lambda and immediately calling it. Most of the time people are like, why do this? Just assign 5 directly. The reason we do this, the most common reason we do this is because we want to have something const, but initializing that thing is not const. So once the variable is initialized, that variable won't change for its entire lifetime. But during the initialization, we need some way of changing the variable during initialization. So in this case, I have taken a dummy example of storing a string version, which will be const. So reading from which we'll read from a file. reading from a file is not a constant operation because we change the string, right? So if we use immediately invoke lambdas, we can have the version string which will remain const, and we'll assign it to a lambda that we'll immediately invoke. In that lambda, I create an if stream, which is an input file stream, and I open file version from the current directory, and then I declare a string which is not const, and I call it file content, and I read the content of the if stream into the file content, and this is the reason why file content cannot be const. And then I just return the file content, and then I am printing the version in this case. So you see file content is not const because it cannot be const because it is reading from a file, but the final result, which is the string version, is const. But this was just the boring part, just to get just to ensure everyone here understands what is going on. The actual part starts from now, and this is a disclaimer. All code beyond the slide will poison your brain. Don't do this at work. Everything from now on is going to be very philosophical, very abstract, and impractical. Don't do it. But this is just for fun. Don't do it at work. His name is Alonzo Church, and does anyone here know Turing, the person after whom the Turing Award is named? Alonzo Church was the advisor, I guess it's called, when Turing was doing his PhD on the halting problem. Does anyone now connect the dots? Do people know the halting problem? So he's a mathematician actually. He's not a programmer, but he invented something. He invented Lambda Calculus, which is the thing that we are going to explore today. This was invented by Alonzo Church in 1940s, and in this programming language, it is a Turing complete programming language. Okay, it has everything that you would expect a normal programming language to have. But this programming language only consists of three things. So you have functions, you have variables, and the only thing you can do with those two is that you can call it. Think about C++. The only thing we can do is we can declare variables, which are immutable, by the way. You cannot, after assigning a value, you can't change it. So you have variables, you have functions, and the only thing you can do is call a function. And further, we have restrictions. There are two more. So functions can only have one argument, and we can only have one return value. And you are thinking, even a very basic function like add needs two values. How are we going to implement a Turing complete language using only these two things? If you only have one function argument. And the answer is currying. Currying was named after Haskell Curry, and Haskell Curry is also the person after whom the language Haskell is based. It is a functional programming language, and the idea is essentially this. So if we have a function that takes foo, and it has two parameters a, b, and we just return the sum of a and b. So this is normal C++, right? If I call foo with 1 and 2, I get back 3. The idea is this and this is essentially the same. So the idea is we'll have a function which will take the first argument. It will return a function that will take the second argument, and that second function will do the actual computation. So if you see actually, when we are calling foo in the first case, we are passing it two parameters 1, 2. In the second case, we are calling foo with 1, and that expression gives back a function, and then we are calling that function the return function with the value 2. There is no comma over there. So do you understand? The important thing is we are calling foo with 1 first, and then we are calling the result of that expression with 2. There is no comma. That is very important. These are two separate functions. Make sense?
Yep.
Yeah. Any programming language kind of has numbers. Like if you don't have numbers, what will the computer represent? Because the computer only has zeros and ones. But Lambda calculus does not even have numbers. We invent our own. So let's see how we can do that. So Alonzo Church defined 0 as doing something 0 times. That is, not doing it. Similarly, 1 is defined as doing something 1 times. 2 is defined as doing something 2 times. 3 is doing something 3 times, and so on and so forth. Does this make sense? Like, this is kind of weird mind-bending stuff, but like it's like to count till 3, what I'll do is I'll have 3 books, I'll place one, so I've done something 1 times, that 1 book. I'll place the second on top, that is 2 times, and I'll place the third one on top of it. I'm doing something 3 times, that's why the books are 3. The way we do it is 0, I'm defining 0, that is a lambda, that takes a parameter f, which returns a lambda that takes a parameter x, which returns x. In this case, f is a function, x is a value. What we are saying is we won't call x, that is, we will call x 0 times. So 0 is a function which does not call f, that is, it calls f 0 times. That's why it's 0. Similarly, this is 1. So 1 is a function that takes a function f as a parameter. It returns a function that takes an x, and it returns f of x. In this case, we are calling f once. That is, we are doing something 1 time. So 1 is a function which calls f 1 times. That's why we are doing something once. That's why it's a 1. 2, similarly, we have a function that takes an f, which returns a function that takes an x, and it calls f of x. Does this make sense? We are calling f 2 times. So we call f of x. Whatever is the return value, we pass it again to f, and whatever that returns, we return as the result. Does this make sense?
Hi, Hemil. I have a question.
Sure.
Here, there is a restriction on the input parameter of f, right?
Yeah.
Okay, so it has to be the same as fx, right?
It does. I didn't get that. It doesn't have to be same as f or x.
No. See, f is taking the fx, right? So now if let's suppose fx is double, then f has to take a double on it, right?
Yeah.
Okay.
Okay, so lambda calculus is not typed. There is
I understand it's not type. Sorry, I understand it's not type, but to work from line number 1 to line number 5,
That's
I need
true.
to have that constant, right?
That's exactly why I have used auto everywhere. Because auto makes it a lambda in which because of which I can use any type. Does that make sense?
Okay.
So
So
when the
original. Okay, yeah. Sorry, go ahead.
yeah,
Go ahead,
sorry.
go ahead.
So the second instantiation of f would take a lambda instead of a number if we gave some number to like let's say f was some function which was um, um I guess
Okay.
I'm not clear with my question. Yeah,
No,
like
no,
the
you
first
can think out loud.
uh, so the first instantiation of f would be different from the second one here
Okay.
because first one would be taking x as an input and the second
No.
one would be
F always takes x as an input.
okay.
F of x will return you x, some of the same type.
Oh, okay, yeah, was having mhm,
So
okay.
f will always x is any parameter, and f will always take one parameter, and because there are no types in lambda calculus, you will always get a valid result, something.
Yep.
So f of uh, 2 is a function which again calls f 2 times because it is 2. So, and so on and so forth. But how to use these exactly? So we are going, this function is not in lambda calculus. Lambda calculus does not have the concept of integers and addition of integers, but we are going to do this, and this this slide is borrowed from Kevin Henny's talk. He called it +1. I'm calling it add1 because you need to change something. So add1 is a function which takes an x and returns an x plus 1. This is the function that we'll use in place of f. As a parameter, we need a function, and we'll use add1 as a parameter. So you will see how this makes sense. So the way this is called is we only have one parameter. So we call 0 with add1, which is a function. 0 of add1 returns a function, and we call the return function with the value 0. So this will print 0. 1 calls f of x and returns it. So add1 of 0 will be called, which will print 1. And then 2 calls add1 twice. It will be add1 of 0. Add1 of 0 is 1. So add1 of 1 will be 2. The output of this thing will be 0, 1, 2. Then how do we actually, we can go crazy with this, right? Because it's our own number system. Let's say we want a number system to start from 2. Let's say I don't want 0 and 1. I can just be like 0 of add1. I can give it parameters 2. Now our number system starts from 2, 3, 4. Because it's our own, I told in the earlier slide, we invent our own numbers. Because it's our own, we can be like, yeah, I want to start from 2. I want to start from 9. I want to start from 13. It's your number system. We can do other funky stuff. Like let's say I only want even numbers in my number system. So I start from 2, but now my function is add 2, which returns x plus 2. It's our own number system. I only want even numbers, so I only have even numbers, 2, 4, 6, 8, and so on. Now we can think of number systems in a different way. Instead of 1, 2, 3, 4, we can be like 1 is the successor of 0, 2 is the successor of 0, and 3 is the successor of 0. Does this make sense?
Yeah, this analogy makes much more sense than +1.
Right?
Yeah.
We'll define this. All of this is actually compiling code. We'll define successor later, but I just we'll get there. 1 is the successor of 0, 2 is the successor of 0, and 3 is the successor of 0. So instead of that, we know that 1 is the successor of 0 and 2 is the successor of 0. So we can replace successor of 0 with 1 because 1 is the successor of 0. So just like 2 is a successor of 1, 3 is the successor of 0, and 2 is the successor of 0, as we see in the last slide. 2 is the successor of 0, and 3 is the successor of 0. So we can write 3 as the successor of 2. Does that make sense?
Yes.
Yeah, great. You guys are great. I took really long time to understand these things. So here is successor. It is defined as a function which takes a function, which returns a function which takes an x, and it calls f of n times f of x, and then it calls f of x once more. That's why I told you successor will confuse this. So let's take this with an example. Successor essentially means, successor of 0 means call 0 one more time, call f one more time after 0 has been called. So if successor gets a 0, it will call 0 of f. 0 of f of x will be the replacement. So 0 of add1 of 0. Okay, wait. Is there? Okay, yeah. So 0 of add1 will return a function that takes an x and returns an x. Does that make sense? Remember?
Yeah, that we remember.
Can you repeat?
Yeah, this part we remember, the 0 to 1.
Yeah. So now we take that result and we call f with that result again. So when we give the value 0, 0 of add 1 of 0 will return us 0. And now we call add 1 with 0. So we are essentially calling f one time when the input parameter is 0.
Okay.
Similarly, if instead of 0, so the second one is successor of 1. So if instead of 0, if I give n, if n equals 1, so 1 of add 1 of 0 is 1.
Kind of makes sense in an abstract way, but would this? I'm still wondering if this would compile or not.
This
Like
does compile.
this compiles, like it will. This fourth line
You know
will
what?
call.
Let's do it live. This compiles. I've written compile. There's no code in this entire presentation that doesn't compile.
Okay, I have one question.
Yeah, sure. Go ahead.
So if you have to call success lambda, you have to call like 3 times in bracket, something like this.
No.
Like I have posted
Where did you post?
in meeting chat meeting.
In the chat.
Yes,
Yeah.
that's one.
No. The way it works is because the first parameter itself is a function which calls that successor.
Yes.
So if the successor is 0, it will. We just have to do this. We just have to write. This is compiling code. So 1 is a lambda which returns which successor of 0 returns. This is the
Okay.
way you call successor.
Okay. Please show the like successor definition.
Here's the definition of successor.
So you are returning it 3 times, so it means a successor contains a lambda, and you still have to call the lambda.
That's not true, because calling the lambdas will get you the next results. We don't want the next result. Successor of 0 will be a function which will be equivalent to 1. When we actually get down to using, remember before this, in the slide, this is how we were using 0, 1 and 2. So when
I'm talking about success lambda, not 0 1.
No.
So
Successor of 0 will give you a function which will be equivalent to 1. So the way you call 1 will be remain same. So 1 of add 1 of 0.
Okay.
Successor will give you a lambda that will be exactly equivalent to 1. Successor of 1 will give you a lambda that will be exactly equivalent to 2.
Okay.
And you use it the same way, exact same way.
I'm still confused.
This is confusing topics. You will like
Yes.
if you want, you can search about Lambda Calculus after this talk, and you will get more about it. There is a lot more depth than what can be covered in this talk.
I think,
So here-
Hemil, sorry to interrupt one more
Yeah.
time. These successors are not actually giving us values. They are giving us some lambdas back
Function.
to us. But
Right, yeah.
but then we again have to use our earlier 1, 2, 3, 0,
Yeah.
1, 2 lambdas and put this successor values into it to get the actual values, right?
That's true, because Lambda Calculus does not have numbers, so there is no concept of returning a number.
Yeah. Yes.
That's why the
Functions
syntax
are first-class citizens.
functions are the only citizens. Right? So
Got it.
here's 0. This is compiling code again. Here's 0. Here's 0. It takes a function f which returns a lambda that actually I don't need this. It returns a lambda which takes an x and returns x. Here is successor. I have commented 1 and 2 because I already defined it below. So successor is a function that takes an n. It returns a lambda which captures this n and takes an f, which returns a lambda that captures f and n both and takes an x. And this is exactly the same as you saw in code, f of n of f of x. n of f will give us a function, and we pass that function x parameter to get back a result, and the result that we get back we call f one more time. So if n is 0, n of f will call f 0 times, and f of that result will call it 1 once. So if n is 2, if n is 1, it will call f once, and we are returning the result of calling f once more. So it will be 2. And if n is 2, we call f twice in this expression, and then we again call f once more. So n is the return result will be equivalent to 3. Right? Here is 1. We need to use autos because we are returning lambdas. Lambdas don't have a type. So what I'm doing is I have defined these values now, and I'm just printing 0, 1, 2, 3. This we have already seen in the slides. So if I compile this, you see 0, 1, 2, 3. Look at this example. So I'm defining 1 as a successor of 0.
Yeah.
In this case, I'm calling this successor function where n is 0.
Okay.
So here's what I'm doing in effect. I'm saying at the end, when I'm printing this 0 of add 1 of 0, what I'm essentially saying is I want to call f of 1 of x.
Okay.
But 1 has not been defined yet, so it is giving me a compiler error right now. I use 1 of f of x. Sorry, my bad. 1 is a lambda that takes a function and calls it once with the second argument. So 1 calls f of x and returns the value, where f is this and x is this. Does that make sense?
Correct. Yeah.
And then 1 of f of x will give me a value. I'm calling f again with that value that was returned by 1 of f of x. So I'm in effect calling f twice when 1 is the input. Let's go back to the presentation. Does this make more sense now? Successor. Does the successor function make sense?
Yeah.
If it doesn't, it will. If you sit down with a pen and paper and evaluate it by hand, then it will. Yeah. Sorry. Go ahead. Go ahead.
I think if we run this code inside that, there was the one tool which gives us the instantiations of the lambdas.
That will actually confuse you because there are lots and lots of instantiations.
Yeah, but at least we will see that it is not recursion that's happening.
Here's the thing. What I'll do is I'll try, because I don't have a pen and paper with me, I'll write it in Paint and we'll see if that makes more sense. Does that work?
Yep.
Let me zoom in a little bit. Let's see. Right. So the successor function is essentially a function that takes 3 parameters, n, f, and x. This is what we return, right? Makes sense to everyone? This is the successor function. We have 3 parameters essentially, and we are calling f of n of f of x. In this case, f of x is going to be add 1. Okay? F equal to add underscore 1, which is a lambda, remember? Does that make sense?
Yep.
X is going to be 0. So n, let's assume n equal to 0. So n is equal to not the 0 function, ZERO. I want to, this evaluates to add 1. Here's the formula. Instead of f, I wrote add 1. Instead of n, I wrote 0. And instead of x, I wrote actual 0. Everyone is with me?
Yeah.
Yep.
Yeah.
We already know that 0 of add 1 of 0 is 0. Is there any confusion in that?
No, this is clear.
So instead of this, I can write it as add underscore 1
No, 0.
of 1.
Oh, sorry.
Yeah. This, what will be the result of add 1 of 1? Add 1 is a very simple function. Here is add 1. Where is it? Where is it? Come in this. Add
It
1
will
is
just be 2, right? It will just be 2.
It will be 2. No. Wait. Sorry. Really sorry. There is my bad. 0 of add 1 of 0 will actually be 0.
Yeah, that's what I said, right? And I
Right.
said sorry also.
No, actually
Yeah.
it was my error. 0 of add 1 of 0 is 0. So add 1 of 0 will be 1. Now think about what we have just done. 0 calls add 1 0 times. What we have just done is we have called add 1's 0 plus 1 times.
Yeah.
So we have called add 1 time, which is exactly the same as the function 1 which we earlier defined.
Yep.
Makes sense? So if you look at it here, 1 calls f of x once and returns the result. So it will call add 1 with the value 0, which will give us 1. So 1 and this 1 and the successor, the second one which we defined as successor of 0, both those are same. Does that make sense? Both those functions call f of x once. Does that make sense?
Yes.
Yeah. Now, instead of 1, let's say, where is the eraser? Here is the eraser. So now let's assume f is actually, okay, wait, sorry, not this one. This one remains as is. F is still add 1, but instead of instead of n is equal to 0, let's have successor of 1. Yeah. Now we'll get back 2. So now instead of 0, I am calling, right? So instead of 0, I have 1 here. Sorry. Forgive my bad handwriting. So this evaluates to add 1 of add 1 of 0. Any confusion in this?
No. Now it will totally
Yeah.
give us 2, right?
Yes. So we already know 1 of add 1 of 0 will be 1. So this is essentially the same as add 1 of 1. Add 1 of 1 is 2. Now again think about what we have just done. 1 will call add 1 once. What we have just done is call add 1 twice. Hence, it is essentially the same as the 2 that we earlier defined because it calls f, which in this case is add 1 twice. Is that better?
Yep.
Yeah, sorry, go ahead.
No, I was just agreeing. Yeah.
Yeah, is it like clearer? It will get more clear when you actually substitute the values by hand. My handwriting is really bad and this is a computer, so like, yeah.
Yep.
Yeah, it's much more clear compared to previous textual representation.
So can we move ahead?
Sure.
Yeah. Now what about Booleans, right? you need Booleans. You don't just execute a sequence of code. You need to make a decision. If the number is even, do this. If the number is odd, do that. If the password matches, do this. If the password doesn't match, do that. Yeah. So, but we only have functions and variables. We don't have ifs. What about Booleans? Like, again, we invent our own. So if this is a sample if condition, if the condition is true, we evaluate the first block. If the condition is false, we evaluate the second block. Does this make sense? Normal C++.
Yep.
Yep. The same thing. If the condition is false, we skip the first one and we just evaluate the second one. Good enough?
Yep.
Yes.
Now, go back to this one. If you look carefully, you can think of true as a function that takes two blocks and executes the first one.
Yeah.
True is just a function that takes two blocks and executes the first one. Similarly, false is just a function that takes two blocks and executes the second one. Does that make sense?
True. Yeah.
Yeah. Hence,
Yeah, it makes sense. Nice.
we can define true, and I have used true underscore because true is a keyword in C++. So true underscore is a lambda that takes an f, that returns a lambda that takes a g, and it will return f. So in this case, we don't call f, but we'll call the result of f, and after that, when we call it, it will actually evaluate. Does
Makes
this make sense?
Yep.
We need to do this because, again, in lambda calculus, we don't have two parameters, we only have one. So we return a function that takes a second, and we just return f.
Yeah.
Yeah. Similarly, this is false. It takes an f that returns a g. It takes an f that returns a function that takes a g, and it returns the g. It does nothing with f. We have two blocks. We pick the second one and we return it. Make sense?
Yep.
Here's how you do it. So if you have true, here's how you use it. So you call it with a lambda, which does the thing that you want. Let's say I just want to return x is even. After that, you give it the second parameter. Sorry, excuse me. You give it the second parameter, which is which in this case is a lambda that returns x is odd. The result of this entire thing till now will return a function which we can call to get back the result. It won't give us the result. It will give us a function that which we call will give us the result. So we immediately call it. Does this make sense? Yeah,
So
go ahead.
do we need to pass something in this?
In what?
Like the last parenthesis?
No.
Oh, so does this return a function or does this return a value?
This true returns a function which returns a function, but at the end, when we call this over here, the last two parentheses, that will actually give us a value.
Okay.
So any guesses on what this expression will evaluate to?
True.
This is already true. We are already using it. This expression will give back a string. Which string will?
Right,
Which will
X is even, right?
X is
exactly.
Even. Yeah.
The same thing. If instead of that, if we use false, everything else is exactly the same. Just instead of true, I'm using false. Any guesses on what this will print out?
X is odd.
Yeah, X is odd is exactly the answer. So the way this actually works is comparisons in lambda calculus return either true or false. Not the C++ true or false, but the true or false that we just defined.
Okay.
And so if let's say lambda calculus had a mod, so if x is even, then x mod 2 will return the true function. And then we can give it the two parameters of what we want to do if x is even or if x is odd. Does that make sense?
Can you use it in a more some useful way instead of directly calling here?
Like if
We would need
like
language support for this. So essentially, let's say, okay, let's say I have a function. Let's say I have a function auto is even. We will it takes an integer. I'll use auto for consistency, but this is an integer, right? If what essentially happens is that the language has to be like, if I mod 2 is equal to 0, I will return did we okay, I'll uncomment this and I'll define is even here. True, false. So what the language runtime has to do is it needs to evaluate condition. If this condition is true, it needs to return the true function that we just defined. Otherwise, it needs to return false. And why does this not compile? Because we need to. Does this make sense? Like if I print the way this will, okay, I already have it. So if what I do is, if instead of x, I am like is even of 2, yeah, we can't actually write this in C++ because true and false are two different types and a function can only have one return type. Is there a way to specify the return type as a std function? Let's check. It will return a function that will take true का type क्या है? That will take a function. It will return a function that will return a function. I am not sure if this will compile in C++.
Still to a decal type of true maybe.
No, actually, because the problem is true and false are two different lambdas, so they have two different types.
Right. Yeah.
So this returns a function, which is a function that takes a function. This will be, I don't know if this will compile in C++. Sorry. C++ has its limitations. I don't know. That will be, I don't know if I can make this compile in C++. But essentially the language runtime will have to do this. So if the condition actually evaluates to true, instead of giving you the keyword true, it will have to return you the function true, which you can then use like this. It will be like is even of 2, and this expression will evaluate to x is even, and if I give it a 1, it will evaluate to x is odd.
So there is one way that maybe you can use a ternary operator. That way the auto evaluate would work.
That still won't work because true and false are two different types because they are lambdas and each lambda has its own type.
Yeah, so then auto would reduce that lambda rate.
But if okay, I can try that as well if it works well and good. So if I mod true equal to 0, I want to return true, otherwise I want to return false. Let's see if that works. Incompatible types. Yeah, it has the same error. True and false are different types.
Oh, okay.
I can't write this in C++ as far as I am aware. If someone is, then please let me know. I'll change my talk. Yep.
Just a thought. What will happen if you pass is even to true or false?
Is even takes an integer for our purposes. Function.
No. The true can take is even function, right?
True will take any two functions and return the first one.
Okay.
If you give true 1 and 0, it will return you 1.
Okay.
True is blind. It just knows that it gets two parameters and it returns the first one. It doesn't do anything special.
Yeah. Okay.
Here's the error, right? So I need other runtime support for this. I can't do it in plain C++, but this works. Trust me, this does. Because is anyone familiar with Smalltalk?
C++ is predecessor.
Kind of.
Yeah.
C++ was actually more influenced by Simula than
Yeah.
So Smalltalk.
Sorry.
Yeah. Go ahead.
For the return type, can we just try like it is a pointer to the function? Is lambda function returning as a pointer?
I don't know the syntax. Can you give me the syntax of like? Can you type that in chat of what you're thinking?
Void star.
It will need to be
return
a function
type as a void
right?
star.
Okay. If we let's see. Does this work? Yeah, but then this will yeah, it won't by default do this. There's no good way to express this in C++ as far as I'm aware, but this will be the thing. Instead of true and false, the essence is instead of true and false, you get functions true and false which do their own thing. It's not a built-in type. Boolean is not a built-in type. It's the essence. You can build Booleans on top of functions and variables. And as you can imagine, it is not the best, like it's not the most efficient way to do it. Again, getting back to where I was, Smalltalk was kind of the second object-oriented language, but it had similar, if you think of it, was essentially taking the idea that we are doing this, there are multiple procedures which are kind of doing the same thing. So let's bundle them up into a class. Class is a mathematical term. It came from maths. So for example, integer is a class of a set. Real numbers is a class of a set. That's how the word class came in and not type. That was similar. Smalltalk was actually one of the major contributors. The original idea of Smalltalk was Alan Kay's, and his idea was that we want to solve complex problems. The way we can do it is, let's assume we have mini computers that are connected with each other and that can use each other to perform independent tasks. And we can each of this computer will be responsible for one thing, and it can communicate with others if it needs help to do something else. Now, in this case, each object is essentially a computer for Alan Kay, and it is connected in a network. And if it wants to, it does one thing. If it wants to do something else, it can reach out to some other object and it can ask it to do something else. That was the original idea of Alan Kay. And in Smalltalk, Boolean is a class and it only has two objects, and which is true and false. So even in Smalltalk, Booleans are not built in. The way this works is essentially the same. It has one method which takes two more lambdas, and true calls the first lambda and false calls the second one. Exactly this. Except in this case, in lambda calculus, it's not an object, it is a function. Does that make sense?
Yep.
Yeah. So this is like, we have invented numbers, we have invented booleans. Let's kind of do something with it. Let's build data structures. Here's how you build a pair. It takes pair as a function, because everything is a function, which takes an x is the first value, which returns a function which takes a y is the second value, and we return a function that calls f of x, and on the result of that expression we'll call y. We'll pass y to the result of that expression. Does this kind of make sense? We'll see the examples, so it will be better. But do you kind of get what we are doing?
Yes.
We have a function, we capture the first and the second values, and we return a function that calls itself, that calls f of x, and to that return function it will call y. And this last return, we need to be able to access the first and the second value. We'll see why we need that. Make sense? Is this confusing? Does this make sense? Like, I don't know. I don't have your cameras on.
Yeah, this makes sense.
Yeah. Let me get to the examples first. Here's how you declare a pair. So I create a variable 1, 2, and it is the pair of 1 and 2. Makes sense?
Yeah.
And we'll define first and second, and those functions, first and second, will give us the values for 1 and 2. Let's come back to first here. So first is a function which takes a pair, which was defined over here. And if you look, we gave pair only 2 values. So essentially the value of that pair is a function that takes an f, and it calls f of x of y. 1, 2 is a variable that takes an f, and it calls f of x of y. Does that make sense?
Yes.
The way we access the second is that we give pair, which is a function which takes a function, and we give it the function which takes an f, and it returns a function that takes a g, and it returns the f. So if you remember, we call f of x with x is the first value. So we call pair, and in this case again f will be the first value, and then again to the result of this expression we call y. So pair, the first the input to pair is a function that takes an f and returns a lambda that takes a g. So we take x, so in this case x will be f and y will be g, and we are returning f, which is x, in this case 1. If the pair is 1 and 2, f is 1, so we return 1. Does that make sense? You can take your time, have a look. If there is a doubt, you can just unmute and just speak. Devashish?
This is kind of like true only, right? Returning the first function. This is like that function we define true.
And you predicted my slide. We can also write first as pair of true. because it has the exact same semantics. Does that make sense?
Makes sense.
Can you go back one more slide?
Let me know when you're done. This is confusing.
And can you show how you are using it in the previous slide, I think? Okay.
Pair of one of two gives back a function which calls that function. I can pass one another function to it, and that will give me the values x and y. So essentially what I'm doing here is f is x, g is y, and I just return y, x, sorry, because that's the first value. That's why we need this part. Otherwise we already have captured x and y both.
Yeah, okay. I mean, it's not very easy to follow with two different definitions being into different slides, but I can.
But the problem with squashing them to those two on one was that you won't have space to think about like both. It's very confusing when slides have a lot more code than 10 lines. So yeah, sorry.
Yeah, I can understand.
Right. So essentially what I'm doing is pair. When I take this pair, I get a function f, and I call f of x, and that returns me a function, and I call y to it, because lambdas can only have one argument in lambda calculus. So this f is the first argument and g is the second argument, and in first function I only care about the first argument, so I just return f. Makes sense?
Yes. Can you also show what will be the output there?
The output of this will be 1 and 2.
Okay, fine.
So getting back to just as Jay Shankar said, this part we have already seen this. This is exactly the same as true, because it takes a function f that returns a function that takes a g and returns the f. This, if we go back, is exactly this. I have a function f that returns a function g that returns f. Make sense?
Yep.
So instead of that lambda expression, we can also write first as the pair of true, because true is also a function. That whole thing still compiles. Does that make sense?
Yep.
Similarly, second is a function that takes a pair and it calls pair with the argument first f, which is the first argument, and g, which is the second argument, and it returns the second argument. In first, we were returning f because we wanted the first value. In second, we are returning g because that's the second argument, which is the second value. Make sense?
Yep.
And that, if you look at it, is exactly the same as false. I have a function f that returns a function g that returns g, and that is exactly what we had here in false. I have a function f that returns a function that takes a g and that returns g. Make sense?
Yep.
Coming back. So g is essentially pair of false, and now if we get to using it, I have declared a pair of 1 and 2, and that's lambda, so I still need to use auto, and I call it 1 2, and I just print first of 1 2 and the second of 1 2, and the output will be first is 1, second is 2. Does that make sense?
But can you quickly jump back to the definition of pair? This
Definition of pair. Yes, pair. Yeah.
Okay. So if we substitute, if like we passed the integer one, instead if we pass the function we defined as 1, that would also give us the same output, right?
We'll need to call that with add 1 of 0.
Yeah. Then this will work.
Yep.
Kind of beautiful.
It is.
Yeah.
The thing is, because lambda calculus has no types, it works with anything. You can pass in a function, you can pass in a double, you can pass in a string, it's the same thing.
Yeah.
So do you want me to go over lists, or is this enough lambda calculus? Because we are kind of already half an hour over time.
You can like give a little overview.
Yep.
Okay.
But yeah.
Let's.
Because you already showed how you can.
Yeah. And let's create a new file. I don't want to erase this entire thing. Right? We can't implement vectors, but what we can implement is linked list. So what we'll do is I'll draw a small diagram. So let's say this is a list with this. It has a pointer to the second element, which is itself a node. So each rectangle is a node. In linked list, you have the element and then a pointer to the next one, right? Everyone knows linked lists, I hope.
Yep.
Yeah. So this third is the last element, so this pointer is null. Everyone understands this? I have a linked list. First element is 1, points to the next node. Second element is 2, points to the third node. Third element is 3, and the list ends. Everyone understands this?
Yeah.
If you think of this node over here, that node is essentially a pair of the element and the pointer to the next node.
True.
Each node is a pair of the current element and the pointer to the next node. And if I look at it like this, let's assume this first node did not exist. Essentially, the 2 and 3 are a separate list in and out of itself. It is an independent list. Does that make sense? Now, given the fact that a node is just a pair of the current pointer and the of the current element and the rest of the list, because we have established that the pointer is because if we break it down, we essentially still have a list. We still have a list of 2 or 3. So in effect, what we have is 1 is a pair of 1, the number, and the rest of the list. Does that make sense? This linked list is essentially, the first node is essentially a pair of 1 and the rest of the list.
Yep.
2 is essentially a pair of 2 and the rest of the list. Make sense?
Yeah.
It is neat when you think about it. And 3 is still the pair of 3 and null, which denotes that there is no more elements in this list. Make sense?
Yeah.
We already have a pair.
Yep.
This is how we implement a list. I'm using nil just as a way to differentiate with false. You can use any value, but Lambda Calculus does not have a concept of nulls. So this is just a special, this list is essentially an empty list. That's it. That's all you need to create a list. Make sense? Does that make sense?
Yeah.
So I accessing either one of them will just give us
False.
yeah like yeah second
Yep.
thing. Yeah.
The way you add an element is also very similar. You take a list, you take that returns a lambda, that takes an x, and you just create a new pair of the x and the existing list. Did that click? Here we are inserting the element of the linked list in the beginning. So if you think about it, let's say I have a list, I have 2 and 3. Let's say I have this list 2 and 3. Does this make sense? Let's assume we have this list with first element is 2, second element is 3. Is that cool? Anyone
Yep.
there? Yeah. Yep. Let's say we want to add one. What we are doing is we are creating a new pair because we have already established the list is just a pair of the current element and the rest of the list. To add an element to the beginning, all we need to do is create a new pair. The first element is the current element and the second element is just the rest of the list. Make sense?
Yeah, a little bit.
Yeah, kind of abstract.
Very abstract. Here's how you use it. So list 1 is an empty list. And remember, you can't change the values of existing variables. Lambda calculus, everything is immutable. You can't change anything. Once it has a value, it will have the same value for the rest of the program. So the way I add an element is I get back a new list, I call it list 2, and I want to add 1 to list 1. Does this make sense? List 2 will be a list that will contain 1 and nothing else.
Yes. No.
List 3 will be a list containing 2 and the rest of the list which will be 1 and nothing else. List 4 which will be the value 3 and the rest of the list 3. Make sense?
Yes.
So if I have, yeah, sorry,
Yes,
go ahead.
sorry.
Go ahead.
Yeah. So if we call in this case first of list 2, we'll get 1.
Yes.
Okay.
And if you want to see this diagrammatically, let's say here, okay, let me go down and see. Yeah. Here's what we have. First, we created an empty list which will be nil and nil. Then we inserted 1. This makes sense? We created a node, we inserted 1 and nothing. Is that like okay?
Yes.
Now I added another node in front of this existing one. Essentially what I did was, this is 2, and the second element of the pair is the existing list, which is list 1. Make sense?
Shouldn't there be an empty node at the end? I mean,
yes, there is an empty node. I didn't have space to draw it.
Okay.
This X represents that this points to an empty node.
Yeah.
And finally, when I insert 3, I create another pair. The first element is 3. The second element is the rest of the existing list.
So essentially 4 nodes are there in this list.
Yeah.
Yeah.
I need a way to mark that this is the end of the list. So yeah. Right. Because I don't have a concept of null, so I need a separate node to mark that this is the end.
Yeah, makes sense.
And the way you access the elements is, to access the first element, you use first of list 4. Does that make sense? Does this make sense that we have a pair and the first value is the first value and the second value is the rest of the list? So to access the first element, we need to use the first function, which we used for pair.
Yeah, makes sense.
Yeah, right.
To access the second element, what we have to do is, the second element of the list 4 is the rest of the list. Come back to this diagram. The second element is the rest of this list. Does that make sense?
Yeah, right. Maybe like if there was a different variable, yeah, it would have been, I think.
That's true, but there is an important concept that I want to demonstrate after in this next slide.
Okay.
That's why it's first of. So what we are doing is, when we access the second, I get back this list. Is that clear?
Right.
Now I have a list, but I actually just want the first element. So the first element of this list is the actual value, and the second argument is the rest of the list. Does that make sense?
Yeah.
So to access the second element, I have to access the first element of the second element of the list. This is the second element. I have to access the first element of the second element of this list to get back my 2. Make sense?
Right.
Yeah.
To access the first element, I need to access the second element of the second element. I need to access the first element of the second element of the second element of this list. The second element of this list is this list, and if I need to access second one more time to get back this list. And now finally, when I have only this last thing, I can access 1 by using first. Does that make sense? That is exactly what I have done here. To access the second element, I need to access the first element of the second element of this list. Make sense?
Yep.
To access the third element, I have to access the first element of the second element of the second element of this list.
Yep.
And this prints 3 to 1. Because we inserted 1, 2, 3, and it inserted at the beginning of the list. So we get back 3 to 1. Make sense?
And if we get the fourth, then we'll get this is false.
Sorry?
Is it? So if we access first of second list 4, that's the fourth element. That will be
The
false.
pair of nil and nil. Yep.
And so that will give us that this is false.
Yeah.
Okay.
I didn't actually implement any checks. If you do it, it will not compile actually, because this is C++ and templates are instantiated at compile time. And do you realize what we have just done? We have a Turing complete language. We can express anything that we want using just three things. We have a function, we have a variable, and we just call the functions. We don't even have our own numbers. We invent our own. We don't have Booleans. We invent our own. We don't have data structures. We invent our own. We have just reinvented Lisp. Lisp is, I guess, the second programming language. It missed 1958. COBOL was the first, if I remember correctly, 1957. And Lisp is based on this mathematical Lambda Calculus. Lisp does not have any syntax. The only thing you can do in Lisp is you can define a variable and you can define a function. That's the only two pieces of syntax Lisp has. Lisp has a built-in pair which is built exactly the way we did. The first is called cons in list. The second is called CDR. The function that creates a list is called cons. The function that creates a pair is called a cons, and a function that accesses the first element of the pair is called char, which stands for content address register. And the second, if I remember correctly, and the function to access the second is called cdr, CDR. Some people also call it cdr or something. And that gives you the second element, and implemented exactly like we did. And once you have a pair, you have a list. And once you have a list, you can do anything, because you can, because if you think of it, a map is like a list of keys and a list of pairs. A set is essentially a list in which we don't allow duplicate entries. Once we have a pair, we have a list, and once we have a list, we have all the data structures, all the fancy trees and everything. Make sense?
Yep.
And that is the beauty, the neatness of Lisp and Lambda Calculus. Lisp does not have syntax. A Lisp program is just a list. Like, I don't know if you people understand it. A Lisp program can reflect on itself and change itself at the runtime. A Lisp program is just a list of statements, expressions, and you can pass that expression to any other function that expects an expression. And once you get that, reflection is just like, it's the obvious thing. Any questions?